So this past time we had the robot questions assignment, which, as you might guess, is full of questions about robots. So question 1, which of the following code options can be used to move the robot, the black triangle, to the black square? So let's just let's walk through each of these and see if they get us to the square. So we're going to repeat 2 times. Move forward, rotate left, move forward, rotate left. So that ends us here after 1 iteration. Second time we're going to go forward, rotate left, forward, rotate left. That gets us back to where we were at the beginning. So definitely not number 1. Repeat 4 times. Rotate left, move forward, rotate right, move forward, rotate right, move forward, rotate left. Okay, so essentially that moves us up 1 square. So if we repeat that 4 times, I'm going to go 1, 2, 3, 4. That will get us where we're trying to go. So option number 2 is our correct answer. This grid contains a robot, a triangle, that is initially facing left. The robot can move into a gray or a white square, but it cannot move into a black region. The program below is supposed to get the robot to the gray square. The program uses gray square reach, which evaluates to true if the robot is in the gray square and evaluates to false if not. Does the following program get the robot to the gray square? All right, if can move right. So what does that can move method do? Remember what that one does? Well, we don't remember. The best place to look is at our quick reference. Let's see if I have it pulled up. It's not this tab. It's this tab. All right, so let's take a look down at robot and see our can move. Can move evaluates to true if there is an open square, 1 square in the direction relative to where the robot is facing. Otherwise, the value is false. The value's direction can be left, right, forward, or backward. So we are trying to check if we are able to move 1 square to the right, if the square to the right is available. Else, so if not, if we can't move right, if we can move right, we're checking that again, then rotate right. If can move forward, move forward. So our first time through, we can't move right, so we're going to move into our next square, we're going to move forward. We still can't move right, so we're going to not be able to move right. We can move forward, so we go here. Then we can move right. So this if statement triggers, we're going to move forward, rotate right. Now, if we're here and we try to move forward, where are we going to go? If we're in this square facing that direction and we try to move forward, we're going to hit the wall, right? Our robot's going to smash into the wall. Let's see what, if we look at our reference, what happens if we try to go past the wall? Yeah. All the way at the bottom. If the robot attempts to move to a square that is not open or is beyond the edge of the grid, the robot will stay in its current location and the program will terminate. So does this code work like we want it to? No, the code is actually going to crash because we're going to try and go out of bounds. So this is just a simple yes or no. No, the program does not take the robot to the red square or gray square. All right, so we have the same kind of grid. We need to know if the program gets the robot to the gray square. So does this code by itself get the program to the, or get the code robot? Does the code get the robot to the square? So before we move forward, boop, boop. If we can move right, which we can, we're going to rotate right and move forward. Boop. Are we in the gray square? No, we have not reached the gray square at this point. So we're here, which is distinctly not the gray square. And since we don't have any kind of a loop here, this isn't going to repeat. We're going to not make it to the gray square in that scenario. All right. Once again, we have a repeat until gray square reached. If we can move right, move forward, rotate right. Else, if can move left, rotate left, move forward. If can move forward, move forward. I feel like we're going to run into the same problem here, where we I feel like this is not indented nicely, but whatever. If we can move right, once we have gotten to this square facing to the right, we're going to hit that same problem of move forward happens before we rotate right. So we're going to hit the wall and crash again. So once again, can't go there. All right, here we have removed going forward from everywhere except the if can move forward. So here, I don't know if we're actually going to have any crashes. So we can't move right, but we can move forward. So we move to here. We can't move right, but we can move forward. So we move to here. We can move right, so we rotate right. So now we are here. Now we can move right, can't we? So yes, we can move right, so we will rotate right. We can't move right, but we can move left. So we'll rotate left. And then we will say since these two ifs are disconnected, we are able to move forward. So we will go to here. We can't move right, we can't move left, but we can move forward. We can move right, so we rotate to the right. We can move right again, so we rotate right. We can't move right, but we can move left. We rotate left. We can move forward. So it looks like eventually we will make it to the end here, as long as we are going to make it. So we will go forward, forward. We're able to move left, so we'll rotate left. We can move forward. We can move forward. We can rotate left, forward, and forward. We will eventually get there, although it will take quite a few iterations of turning and then undoing some turns. So this loop, this code absolutely will get us to the gray square, albeit somewhat slowly. All right, which of these code options will make the robot touch the greatest number of gray squares? So let's color code our paths. Let's say this one is this first one is bright green. Next one is bright blue. Next one is pink. Next one is orange. So let's follow the green. Rotate right, move forward. So that's going to end up here. So that's got 1. All right. Move forward, rotate right, move forward. that's going to touch 2. Move forward, rotate right, move forward, rotate left, move forward. That's also going to touch 2. And move forward, rotate right, move forward, rotate right, move forward. I feel like that's also going to touch 2, unless I've done something horribly wrong. Forward, right, forward, right, forward. Wait. Those won't actually touch 2. We're not moving forward past those squares. So each of the actual, I'm gonna rewrite these. Green will, in fact, rotate right and move forward. So green will end up here. Blue, forward, right, forward. We end up here. We only touch 1. Pink, forward, right, forward, left, forward. We end up here, actually, also only touching 1 square. Orange, we do touch 2. We go forward, turn right, and then forward, touching 2 squares. So option 4 will actually touch 2 squares. I miscounted before. I assumed that we moved forward when we turn right. For some reason, that's not how it works. Rotating, you stay in place. Which of the following code options will make the robot touch all of the gray squares? Move forward, rotate left. It will draw out our path. Green, blue, and pink again. Well, let's look at pink first. Rotate left, rotate left, rotate left, rotate left. That's going to keep us in place. So definitely we're going to touch none of the gray squares there. We follow blue. We move forward, rotate right, move forward. Move forward, rotate right, move forward. We're not going to touch all of the gray squares with blue. We use green, move forward, rotate left, move forward, rotate left, move forward, rotate left, move forward, rotate left. We've touched 2 out of 4, but that's still not all of them. So I don't think any of these are going to actually touch all of the gray squares. All right, same question. Which of these will make the robot touch all the gray squares? Repeat 2 times. Green, orange. We found pink. Is there another one below? Can't scroll over. Try. Okay, perfect. The last answer is none of the above. All right, well, let's look at pink first, because that's the color I have selected. Slightly. Okay. So, pink, move forward, rotate left, move forward, and repeat 3 times. Rotate left, move forward, rotate left, move forward, rotate left, move forward, move forward. Well, looks like that first one we checked did in fact touch all of the gray squares. So I think pink is going to be our answer here. We could follow through with green and orange, but given that that one does in fact do it on our first check, let's go with that one. All right, each gray square in the grid represents a possible final location of the robot after the code segment is executed. Which of the following does not make the robot end in a gray square? Repeat 4 times. Oh, it's actually, no, there's only 3 options. Perfect. Let's color code it again. Pink, green, and blue. blue first, that's what I have selected. We're going to repeat 4 times. Forward, rotate left. Forward, rotate right. So it's 1, forward, rotate left, forward, rotate right, forward, rotate left, forward, rotate right, forward, rotate left, forward, rotate right. So that one will get us to a gray square. Repeat 4 times for green. Rotate left, move forward, rotate right, move forward. Rotate right, move forward. Rotate left, move forward. Rotate right, move forward. That's going to get us out of bounds. Actually, wait. Yes. Yeah, because we were facing this direction at the end of our first iteration. So we're going to go out of bounds with green. So it will definitely not end up in a gray square. Let's double check that pink does get us somewhere. Repeat 4 times, rotate left, move forward, rotate right, move forward. Rotate left, move forward, rotate right, move forward, left, forward, right, forward, left, forward, right, forward. So both of pink and blue get us the same square, kind of doing a zigzaggy pattern. Green goes out of bounds. So definitely the green one. Our goal is for the robot to go to both gray squares. Which program below accomplishes the goal? Pink, blue, green, or none? All right, so let's do green first. Repeat 3 times. Forward, rotate left, forward, forward. Forward, rotate left, forward, forward. That goes out of bounds. Definitely not the green one. Do blue next. Move forward, move forward, move forward, move forward. 1, 2, 3, 4. Rotate left. Move forward, move forward, move forward, move forward. That one gets to both gray squares. There we have it. All right, the robot must get to the gray square at the top left-hand corner without passing through the black squares. Which procedure below accomplishes this goal when executed? All right, our options are both of the above or neither of the above, in addition to these 2 answers. So we're going to have to draw both of these out, green and blue. So green is going to have us rotate left, move forward, rotate right, move forward, and forward 2 more times. Rotate left, move forward, move forward. Rotate right, move forward. Rotate right, move forward. So green does not get us there. Just double check all my steps. Wish you could zoom out just a little bit further. Can I control? Okay. So rotate left, forward, rotate right, forward. Why is that one shorter than the other ones? Oh, there's no space. Got it. So forward, forward, forward. Rotate left. Move forward, move forward. Rotate right, move forward. Rotate right, move forward. So I got us in the wrong place before, but it still does not get us to a gray square. And with our blue option, rotate left, move forward. Rotate right, move forward, move forward, move forward. Rotate left, forward, forward. Rotate right, rotate left. Forward, right, forward. So right, left, forward, right, forward gets us there. So blue option 1 does reach the goal. And our final question. The robot must get to the gray square at the bottom left by jumping over the black hurdle. The program to achieve this is rotate left, move forward, rotate right, jump hurdle, rotate right, move forward. So we rotate left, move forward, rotate right, jump hurdle. So when we jump the hurdle, we will be in this position. And we need to end up in this position so that we can rotate right and move forward. So we want to, let's look at these two options, orange and green. So green, move forward, rotate left, move forward, rotate left, move forward, rotate right. That'll get us into the black square. That definitely will not work. So not green. What about orange? Move forward, rotate left, move forward, rotate left, move forward. That one will get us from the position we need to the position we need. Orange is good. So there are our robot questions for today. Hope that was enlightening. All right, so today there are 2 assignment quizzes. One of them is 1 question long. One of them is 3 questions long. Not very many questions today. But before I let you work on those, we're going to talk about algorithm efficiency and 2 different searching algorithms. So a searching algorithm is an algorithm that we use to find a specific value within a list. So there are 2 primary searching algorithms that you're going to need to be at least aware of. Linear search and binary search. So each of these is going to determine whether or not something is present in a collection. So linear search, let's say we have a sequence of values. Linear search is going to go 1 by 1, checking if the thing we're looking at is the thing that we're looking for. If it ever finds it, it will return the index where it found it. And if it reaches the end without having found it, it'll say, oh, that thing is not here, return -1. So based on that description, do we think that linear search requires the list to be in a sorted order to work? No, this will totally work. Whatever order the list is in, we can just look through each and every element. If we ever find it, we're good. Binary search, on the other hand, does require that the list be sorted beforehand. And the way it works is it's going to find the midpoint of the array. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. The midpoint is going to be at index 4. No, in 5. No, it's going to be at index 4 because we're going to divide by 2. And we want an integer division, so it's going to be 9 over 2 is 4.5. We round down. So with our indices 0, 1, 2, 3, 4, 5, 6, 7, 8. So our midpoint is going to be at index 4, which is the 5th element. So we're going to check, is the value at this position bigger than or less than what I'm looking for? If it is bigger than what we're looking for, we can eliminate that position and everything that comes after it in the list, because we know it's not going to be there or anywhere after. If the list is already sorted, it's not going to be anywhere there. If it's smaller than what or if the thing that we were looking for is too big, if the thing here is smaller than we are looking for, we can eliminate the front half of the array. And we're going to repeat this until we either find our value or until the beginning and ending of what we're looking at are past each other. We've eliminated all of the values. So if we repeat this, let's actually fill in some numbers here so we can actually do an example. Let's say I'm looking for, I have 1, 2, 3, 9, and not jump that big, 5, 7, 8, 10, 15, 12, 15. Let's say I'm looking for the number 2. So is the value at index 4 bigger than or less than what we're looking for? It's bigger. So we know, since this array is sorted, since this list is sorted, the value we're looking for is not going to be at this index or anywhere to the right of it. So we can eliminate all of these indices from our search. So now the smallest index available is 0, and the largest available index is 3. To find our midpoint, we find the average of those two. 0 plus 3 is 3. 3 divided by 2 is 1.5. We round down to 1. So our new index is here. Is this the thing we're looking for? It is. So we have found our thing in 2 executions of the loop, or our algorithm process. So that's just a very brief little crash course on how binary search and linear search work. So let's answer some questions about them. In which of the following scenarios will linear search run faster than binary search to find a target value in a sorted list? The length of the list is extremely large, the target value is in the very middle, the target value is the first value, or the target value does not exist in the list. But when is linear search going to be faster? When it's the first thing, because linear is going to look at every single thing. And since binary starts looking at the middle, it's going to have to make more checks to find the thing at the very beginning. So if the thing is at the very beginning, linear search will be faster. Okay, I apparently am not logged in or something. Which of the following statements are true about the binary search algorithm? Binary search can only be used when the list to search is sorted. Binary search is more efficient than linear search. I think both of those are true. Binary is generally going to be much, much more efficient. Which of the following statements are true about linear search algorithms? Linear search can only be used when the list is sorted. Linear search is more efficient than binary search. Neither of those is true. Given the following search algorithms, algorithm 1, given a song list and a target value song to find, a variable position is assigned a random index within song list. A variable song is assigned the value at song list position. If song equals song defined, return position, else go back to step 1. So we're just randomly picking, and if we find what we're looking for, we return our position. Algorithm 2, given a list, song list, and target value song defined. Step 1, repeat steps 2 and 3 for every index I in song list. If variable song or a variable song is assigned to the value at song list I, if song equals song defined, return I. Step 4, return -1. Will algorithm 1 ever, or it might return the correct position, right? But it's entirely possible that we're going to randomly pick the wrong thing every single time, even if the thing is present. So algorithm 1, I think is pretty bad. So and is it true that in every single case, algorithm 2 will always take less steps to find the target value than algorithm 1? Not necessarily. If algorithm 1 randomly selects the correct thing on the first try, it will take less things. But as our size gets larger, it becomes, I think, decreasingly likely that algorithm 1 will randomly select the correct index. Algorithm 2 is always going to have the same number of executions. It's always going to look at every single thing, where algorithm 1 is going to randomly pick over and over and over again. So I think as the song list becomes larger, algorithm 2 becomes more efficient. And I can't check my answers because reasons. I'm not logged in. Let's fix that. Please hold.
I have to stop sharing.
Okay. As the song list becomes larger, yes, algorithm 2 will become more efficient because algorithm 1 is relying on randomness, and randomness becomes less reliable the more options there are. The table below shows the time a computer takes to complete a specified task on the consumer data of different sized companies. Task A with 100 customers takes 5 hours, with 1,000 customers takes 50 hours, a large company takes 500 hours. So the scaling here, we're multiplying by 10 each time. Task B with a small company takes 0.2 hours, with a medium company takes 2 hours, with a large company takes 200 hours. Task C takes 250, then 350, then 450. We're increasing by 100 each time. And task D goes from 200 to 250 to 300. So here we're increasing by 50 each time. Which of these tasks is likely to take the longest time when we scale up to a very large company of 100,000 people, if we follow these patterns? B. Why is B the answer? Because it's multiplying by 100 each time, right? So our change scale is multiply by 10, just plus 100, plus 50, where here it's times 200, not 200, it's times 100, times 100, which is going to scale up way, way, way faster. So even though tasks C and D initially have a very high amount, 200 times 100 is going to be 2,000, 20,000, which is going to be way, way, way higher than 550 or 350, right? So B definitely scales the worst out of these things. A group of researchers is testing the speed of an algorithm on various inputs. The table shows the time it takes for the algorithm to run on different sizes. Looks like it is increasing by a factor of 10 each time. So if we are given an input of size 6, what might we expect to see? 1 million. If we add a 0 at the end, we get 1 million. All right, same kind of question, but with a different scaling factor. If our input size is 1, our runtime is 1 second. If our input size is 2, our runtime is 4 seconds. If our input is 3, 9 seconds, then 16, then 25. So what is the pattern that we see here. It looks like the runtime is equal to the input size squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So 6 squared is 36. So we should expect to have that take 36 seconds. Our final question, it looks like. Yep, final question. This looks like it's following the binary sequence 2, 4, 8, 16, 32. Next in the line is 64. So, yeah, analyzing algorithms, there is that. Our 2 assignment quizzes for today are flowchart algorithms and simulation and modeling. So I will make sure those are unlocked